Very good. All right. Right now, we're going to start reviewing Chapter 9. Chapter 9, if you remember, was on inferring means from statistics. We're always looking at population means from statistics means. Uh, the accuracy of an estimator is measured by the standard error. Now we got to be real careful. The accuracy, it's actually the precision of an estimator is measured by the standard error. The accuracy has to do with bias, and we're not sure if we're biased or not. Okay, so that one was false. The precision of an estimator is measured by the bias. No, again, this is not the precision, it's the accuracy of an estimator is measured by the bias. The precision is measured by the standard error. So that one was false. A sampling distribution is a probability distribution of a statistic. Okay, and the statistic is usually the population mean, but it can be a proportion. This is true. When a statistic of the sampling distribution is the same value as the population parameter, we say that the statistic is an unbiased estimator. What we're saying here is when a statistic, like an average, okay, in our sample, when they cluster around the same value, okay, we say that the statistic is an unbiased estimator, and that is true. The standard deviation of the sampling distribution is what we call the standard error, and it's the standard deviation divided by the square root of n. The standard error of the sample mean gets smaller with a larger sample size. Absolutely. The more precise, you get a more precise answer with a larger sample. For all populations, the sample mean is unbiased when estimating the population mean. Well, yeah, that's if we have a simple random sample, this is true. Doesn't matter what the population looks like. The sample mean is unbiased when estimating the population mean. When considering the sampling distribution of the sample mean, the larger the sample size n, the better the approximation. And that's true. When considering the sampling distribution of the sample mean, if the population's normal to begin with, then the sampling distribution is going to automatically be normal, no matter what n is. There's no restriction on n then. The sample mean, we know what the sample mean is. It's the arithmetic average that we're used to. You add up 3 grades and divide them by 3. It's an estimation of the population mean, and it's unbiased if we use a good random sample. So all the above. The t-distributions are symmetric, unimodal, and bell-shaped. This sounds a whole lot like a normal distribution, and it is like a normal distribution, except it's a little bit flatter and the tails are thicker. There's a little bit more uncertainty in a t-distribution than a normal distribution. All of these are correct. Compared to the z distribution, the t distribution has thicker tails and a lower peak. Thicker tails and a lower peak. The t distribution shape depends on one parameter, and it's called, well, this is tricky. I would say the degrees of freedom, if we're going to pick one, and that's really n. Degrees of freedom turns out to be 1 minus n minus 1. There's a mathematical reason for using n minus 1, but the degrees of freedom depends is 1 less than n, and that's the shape of the t distribution. It depends only on n, or n minus 1, which is the degrees of freedom. Ultimately, when the degrees of freedom is infinitely large, the t distribution is exactly the same as a normal distribution. This is true. It actually gets pretty close by the time we get to 25 or 30. Confidence intervals are techniques for communicating an estimate of the mean along with a measure of our uncertainty in that estimate. That's a good way of putting it. A confidence interval can be interpreted as a range of plausible values for the population parameter. A confidence interval can be interpreted as a range of plausible values for the population parameter. This is true. The confidence level is a measure of how well the method used, that word method is very important, to produce the confidence interval, how well that method performs. Okay, it will produce a confidence interval that catches the true value 90% of the time, 95% of the time, something like that. This is also true. Which of the following are ways in which we can report a confidence interval? We can give it a lower bound to an upper bound. We could say we're 90% sure that the high temperature today will be between 85 and 95. We can say the temperature is going to be 95 plus or minus 95 plus or 90 plus or minus 5. Uh, C talks about just one item. When we have the standard deviation, that's just one item. The margin of error would be like perhaps two standard errors. That would give you close to 95%. So A is correct and B is correct. C is talking about one item and not an average. Hypotheses are always statements about population statistics. This is true because we know the statistics. We will know the statistics exactly. What we're trying to decide is something about the population. So our H0 usually says that mu, or the population mean, is equal to some value. This is true. Oh, wait a minute. Wait a minute. Let me go back here. Let's see if I'm smart enough to go back. I did something wrong there. Hypotheses are always statements about population. The word that's the problem here are statistics. It should be parameter. It should be parameter. Okay, and the problem is this says This says statistics, always about a population parameter. That's what makes it false. Okay, great. Sometimes they trick me. Which of the following values for significant level alpha are good choices? Okay, if it doesn't matter much, it could be 90%. If I want to be, let's say, let's say I want to make sure that a student has passed the test, I only need to be 90% sure. Okay, I don't have to be 100% sure that he has all the knowledge, let's say 90 or even less. Okay, so at 10%, C would be okay. If it's something more critical, like buying a car, I want to be 95% confident that I'm getting the right car. 5% is okay. How about 1%? Well, if this is going to adversely affect somebody, um, significantly adversely affect somebody, maybe I want to limit it to 1%. Okay, so all of the above can be used for different situations. The T statistics measures how far away, how many standard errors are observed mean X bar lies from the true population value mu. This is true. Oh, something's not right. Oh, let me read this. No, 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 no. You see, they got me again. It's not from the true population value mu, it's our hypothesis. It is from mu zero. Boy, you got to read these very carefully. The T statistic measures how far away, how many standard errors are observed mean X bar lies from the hypothesized population value mu zero. There we go. Every word counts. In hypothesis testing, values of the T statistic that are far from zero tend to discredit the null hypothesis. This is true. The p-value tells us the probability that we would get a t statistic as extreme or more extreme than what we just observed if we repeated the test again. True. There are three basic pairs of hypotheses. Okay, we always have the null hypothesis equal to mu. The two-tailed test can be right either way, and so that's going to be B. B as mu is equal to mu zero, and mu is not equal to mu zero, so there's two ways that can be true. That is a two-tailed test. Okay, the left-tailed test is simply less than. And the right-tailed test is simply greater than. That looks simple. When comparing two populations, if the data sampled from one of the populations are one sample of a related pairs, then they are paired or dependent samples. This can be before and after. This can be husband and wife, brother, sister, something like that. With paired or dependent samples, if you know the value that a subject has in one group, then you know something about the other group too. That's true. Which of the following are examples of dependence? Before and after, when the objects are related somehow, comparing twins or siblings or spouses, when the experimenter has deliberately matched subjects in the groups that have similar characteristics. Okay? All the above. This is D. This is an easy one. This is D. Okay? Didn't quite circle D, but with paired samples, we turn two samples into one. We do this by taking the difference of each pair. We take the after and subtract the before to see what our treatment has done. This is true. And we're going to wrap this up here.